Welcome to the deep dive. Today we're looking into a really interesting area of large language model research, chain of thought, or CoLLaMA reasoning. It's how models like, say, R1 and QWQ manage those complex multi-step problems that really, showcases advanced reasoning.
Yes, absolutely. These extended CoLLaMA sequences, they've really shown a remarkable capacity for problem solving. However, the computational expense associated with training models to generate and, well, effectively use these long reasoning paths is a pretty considerable challenge.
Right.
The sheer scale of resources needed to explore and refine these intricate chains, it's quite substantial.
That naturally leads to the concept of knowledge distillation, right? Taking a highly proficient, maybe resource-intensive teacher model and transferring its reasoning capabilities to a smaller, more streamlined student model. It's about imparting the essence of expert reasoning, but in a more efficient package.
Exactly. And the core question this research we've been looking at tackles is, well, what's the advantage of using long CoT data in this distillation process compared to shorter, maybe more conventional CoTs? The focus is particularly on the efficiency gains and, critically, how well this distilled reasoning ability actually transfers to other models.
And the study takes a deep dive into the thinking process itself for models like R1 and QWQ. They're not just looking at a single line of reasoning, but the more intricate structures that emerge, linear progressions, branching tree-like explorations, even interconnected network paths, all anchored by what they term a core trunk. Think of it as the most direct, essential line of reasoning, maybe with various supporting investigations branching off.
And what's particularly interesting is this observation of overthinking in these state-of-the-art LLMs. They frequently explore multiple solution avenues, and some of those might turn out to be redundant or even incorrect. The worry is that smaller student models could inherit this tendency, leading to unnecessary computations and potentially even a decrease in overall performance.
Right. It's like a student learning from a brilliant but sometimes inefficient professor. They might pick up on the brilliance, but also some of the less productive habits.
Exactly.
And that brings us to DLCoT, the deconstructing long chain of thought framework. This is an automated method specifically designed to process this extensive CoT data for distillation, aiming to tackle these very issues of efficiency and the inheritance of, well, overthinking.
Okay, so let's unpack the initial findings then. One key aspect the research really brings to light is the limited universality we currently see in long CoT distillation methods. They observe that when you distill long CoT reasoning from a model like QWQ, its effectiveness drops, well, pretty significantly when applied to models with a fundamentally different architecture. Think like the LLaMA series.
That's a really important point, isn't it? It sort of challenges the assumption that the information embedded in the reasoning process is inherently universal, easily transferable across any model design.
Precisely.
It suggests that for effective knowledge transfer, there might need to be a closer alignment between the architectural principles of the teacher and the student. So what does this lack of universality tell us about the underlying way different model architectures think? Does it mean we need to be more targeted in our distillation strategies?
It strongly implies that yes. It suggests the way a QWQ model constructs its reasoning might be deeply intertwined with its specific architecture. However, they also found a compelling contrast. When they distilled long CoT data generated by R1 onto the Qwen 2.514b model, it achieved an accuracy level comparable to the QWQ distilled Qwen 2.532b model. This is quite significant because it suggests that long CoTs generated by R1 might possess superior training efficiency and a greater capacity for knowledge transfer, at least within the Qwen family. And the paper visually represents this quite clearly. The performance of QWQ distillation really drops off when applied to the LLaMA family.
So R1's thinking seems more readily adaptable, particularly within its own lineage. That really highlights a fundamental difference in how these models structure their internal reasoning steps.
Moving on to the structural characteristics of these long CoTs, the research identifies distinct patterns, linear, where each step builds directly on the last one. Tree-like, where the model explores different branching approaches. And network structures, which can involve revisiting and integrating information from earlier stages. Figure 2 in the paper gives a clear visual of this, using the simple example of simplifying 2y plus 3y plus 4y to show how QWQ and R1 might explore different solution paths.
And it's quite striking how even for something that basic, these advanced models engage in what seems like pretty extensive exploration and verification. It really underscores this overthinking phenomenon they've identified.
Indeed. Both R1 and QWQ show this tendency to investigate multiple solution pathways, multiple verification steps, including what might appear to us as redundant or even erroneous detours. It's like they're not always taking the most direct route.
Which brings us back to DLCoT, the framework specifically engineered to optimize this process for distillation. Could you walk us through the essential steps involved in DLCoT?
Certainly. So DLCoT is basically a framework for enhancing this distillation data, and it operates through 3 main stages. First, there's data segmentation in breaking down these complex, long CoT structures into more manageable bits.
Okay.
Second, the framework focuses on simplification. This means identifying and eliminating both unsolvable paths and, crucially, redundant solution paths. Finally, it includes an optimization phase that targets intermediate error states within the reasoning chain.
So the core idea is to really refine the reasoning process down to its essentials, removing the unnecessary complexities and detours. It's kind of like editing a detailed mathematical proof down to the most elegant, direct argument.
Exactly. And the primary objective is to prioritize what they call the reasoning trunk. That's the shortest, complete, and correct sequence of steps leading to the answer while discarding those redundant or unproductive explorations. Think of it like finding the main path through a maze, not all the dead ends you might explore along the way.
Got it. And within this DLCoT framework, the research identifies 4 key components that consistently pop up in the reasoning chains of both R1 and QWQ. What are those core elements?
According to their analysis of the logical structure, these are problem restatement and comprehension, where the model sort of reinterprets the question; approach exploration, which involves searching for and executing potential solution strategies. This is the bulk of it, really. Then result verification, where the model checks its answer; and finally, the final answer itself.
That seems like a very logical breakdown, almost like a standard human problem-solving method. And the study went deeper into this approach exploration phase, correct? What were the key insights there?
Yes. Their analysis, which includes things like word clouds showing the language used during this phase, you can see that in Appendix E, Figure 6, it reveals a sort of hierarchical structure within approach exploration. Problem definition is a small part, maybe 3.8%. The vast majority, a huge 84.9%, is dedicated to the approach process, the actual calculations, the steps.
Right.
Verification within the approach accounts for about 6.7%, split between exploring alternative methods and doing stepwise checks. And lastly, a summary of the approach makes up around 4.4%. What's really telling is where these models spend most of their thinking time, heavily focused on the execution of the chosen approach.
It's fascinating to see such a large proportion dedicated to just the core computational steps. It really highlights how critical accuracy and efficiency are in that central part of the reasoning. Now, DLCoT itself uses a more granular 5-step process, as shown in Figure 3. Could you elaborate on those specific stages?
Absolutely. So the DLCoT workflow starts with macrostructure parsing. Here, the long Co is initially segmented into those 4 main components we just discussed: problem restatement, approach exploration, verification, and summary.
Okay.
The second stage is approach and verification parsing. This involves a more fine-grained, LLM-driven segmentation of the approach and verification sections into individual steps. This parsing is done with minimal constraints to really capture the natural flow of the model's reasoning.
So it's not imposing a rigid structure, but rather letting the model's own inherent reasoning flow dictate the segmentation.
Precisely. The third step is redundancy analysis. Here, the framework groups similar approaches and verifications based on defined similarity metrics. And critically, it uses a 3-tier evaluation system, categorizing these steps as erroneous, meaning they lead to wrong conclusions.
Right. Incomplete valid steps, maybe, but they don't actually lead to a final answer, or correct, which successfully reaches the right solution.
That categorization seems fundamental for deciding what to prune and what to keep during distillation. What happens in the next phase, optimized integration?
In this 4th step, the framework uses the information from the redundancy analysis to prune redundant approaches and also eliminate erroneous strategies within the same cluster of reasoning attempts. The main goal, like we said, is to keep the core efficient reasoning trunk, but also maintain a degree of diversity in the correct solution paths.
And finally, there's coherence reconstruction. What's the objective there? After removing the redundant or erroneous bits, this final step involves applying minimal edit rewriting to the remaining reasoning steps. This is to make sure the final distilled output is fluent, logically sound, and maintains its overall coherence. It's not just about chopping things out.
Makes sense. It's not simply about cutting sections, but ensuring the remaining parts connect logically and are easy to follow. Now, the research includes quite a bit of experimental validation. What were some of the most significant findings from those experiments?
Yeah, they ran a series of experiments using benchmark data sets like Numina Math and their own bespoke Stratos R1 dataset. They evaluated their distillation methods on both the Qwen and LLaMA series models. Table 1 in the paper gives a systematic analysis of different distillation techniques. A key finding reinforced QWQ's strong performance when distilling within the Qwen family, but also it significantly reduced effectiveness when transferring to the LLaMA architecture. Conversely, the R1 distillation dataset showed better cross-architecture adaptability. The Qwen 2.514b model, distilled using R1's CoT data, actually achieved performance comparable to the much larger QWQ32b preview model.
Wow, that really emphasizes the importance of architectural compatibility again. And what were the specific findings when they analyzed the impact of the DLCoT framework itself?
Tables 2 and 3 detail those results. They specifically looked at the impact of reducing redundancy. Interestingly, they found that the most aggressive reduction of redundant approaches, what they call the DLCoT multi-nel setting, yielded the most significant performance improvements in the distilled student models.
Okay, so getting rid of redundant paths helps most.
Yes, but, and this is key, when they went a step further and tried to reduce incorrectness by deleting erroneous reasoning paths, they actually observed a slight but noticeable negative impact on the final performance.
That's fascinatingly counterintuitive. You'd think removing incorrect steps would always lead to better learning, wouldn't you?
It is, yeah. And their analysis offers some crucial insights into why this might be happening. Their findings suggest that the diversity and richness of approaches within the core reasoning trunk are really paramount for effective long CoT distillation. Removing unique, even if ultimately incorrect, reasoning paths, or maybe pruning detailed calculation errors too much, can inadvertently hinder the learning process in the student model. It seems the student benefits from observing a wider range of problem-solving attempts, even those that don't initially succeed.
So it's not just about the final correct answer, but also about the very landscape of approaches the teacher model explores, including the dead ends. The student seems to learn from seeing that broader exploration.
Exactly. Figure 4 in the paper plots the average cluster number against the average trie-number per cluster, and it visually represents this idea of approach diversity. The DLCoT multi-setule, setting the one that removes redundancy but not necessarily incorrectness, achieves the lowest slope on this graph, indicating greater diversity in the retained approaches.
I see.
Conversely, actively removing erroneous methods leads to a reduction in this diversity. Furthermore, Figure 5 illustrates the token efficiency gains achieved with DLCoT multi-multi. It shows a substantial reduction in the number of tokens needed to represent the reasoning process compared to the original long tokens.
That's a big deal for efficiency.
Absolutely. They also saw a correlation between problem difficulty and token consumption. This reduction in tokens isn't trivial. It could mean significant cost savings and faster training times, especially with massive data sets.
And the negative impact of removing incorrect steps. The incorrectness failure. What's the proposed explanation for that phenomenon?
Yeah, their analysis suggests that just deleting incorrect calculation steps might disrupt the logical coherence of the reasoning chain. And, perhaps more importantly, it might interfere with the model's ability to engage in self-reflection and learn from its own, or the teacher's, mistakes. It appears that even observing incorrect steps, and potentially how the model corrects those errors, plays a valuable role in developing robust reasoning capabilities in the student model.
That's a really nuanced finding. It highlights that learning isn't solely about exposure to correct solutions, but maybe also about understanding why certain approaches are flawed. Now, as with any research, there are acknowledged limitations. What did the study identify as areas for future work?
They pointed out a couple of key areas. Firstly, they haven't extensively looked at the generalizability of their distillation data and the DLCoT framework across models with really fundamentally different architectures or training objectives. Understanding how these techniques perform on a broader spectrum of model designs is crucial.
Right.
Secondly, they haven't yet investigated the potential impact of DLCoT process data on accelerating progress in reinforcement learning, or RL tasks, particularly for reasoning. It's still an open question whether this optimized distillation data could lead to faster convergence or better performance in RL-based training for complex reasoning.
Those are definitely critical directions for future research. So to kind of bring our discussion to a close, what would you say are the most important takeaways from this deep dive into DLCoT and the nuances of long-code distillation?
Well, in summary, this research introduces DLCoT as a, I think, highly effective framework for optimizing long chain of thought data, specifically for knowledge distillation. It does this by intelligently deconstructing reasoning processes, selectively getting rid of redundancies, while making sure to preserve a diverse and ultimately correct set of reasoning pathways. And the study importantly underscores that the richness of explored approaches, including some that might initially be incorrect, seems to be a crucial factor in effectively transferring these complex reasoning abilities from large teacher models to more efficient student models.
These findings seem to hold significant promise, then, for making the development of high-performing LLMs with robust reasoning capabilities more efficient, maybe more economically viable, too.
Absolutely. And it leaves us with a compelling question for you, our listener. Considering these limitations, how might future research tackle the significant challenge of generalizing these powerful distillation techniques across fundamentally different model architectures? And, maybe even more intriguingly, what potential impact could this kind of meticulously optimized distillation data have on pushing the boundaries of reinforcement learning for tackling ever more complex reasoning tasks? It's clear that while we've made remarkable progress, there are still many layers to uncover in this fascinating domain of large language model reasoning.